Okay, well, thanks, James, for the introduction, and thanks particularly to the organizers for setting up this wonderful workshop. So I'm going to tell you about something very specific that we've been quite excited about recently in the context of leveraging quantum geometry, not in free electron systems, but in interacting electron systems. And I'll try to argue that this is sort of also a natural consequence of a larger theme of thinking about new materials, Moray systems, et cetera, where these effects could be prominent. So let me just give a twofold motivation for this talk in this spirit. So on one hand, within the spirit of the workshop itself, designing materials, particularly out of equilibrium, one motivation is thinking about periodically driven quantum materials, which in the context of free electron dispersions and engineering band structures have seen tremendous progress in the context of, okay, I think the laser pointer is out of order. Well, oh, here, good. In terms of engineering single particle band structures, getting new responses, photo-engineered transport responses, such as the light-induced anomalous Hall effect, or even thinking about pseudospin engineering in black phosphorus. But a more sort of obvious next step is to think about taking these concepts into the many-body realm. And there, of course, we have a plethora of already theoretical proposals of thinking of harnessing light and strong driving to engineer correlated electron states in materials, at least on short enough timescales before the material heats. The general name of this game is thinking about pre-thermal phases in quantum magnets, but also maybe more exotic phases, such as the fractional quantum Hall effect or superconductivity, with a very nice recent demonstration done by the group at Caltech, by David Shea, in terms of flow-K engineering optical nonlinearities in a strongly correlated electron systems. So on the theoretical proposal side, there's an ever-growing example of mechanisms in which we can think of targeting many-body states using tailored excitations. But a key question, of course, within the context of this workshop is thinking about what are criteria that make materials particularly amenable to engineering non-equilibrium states of matter? What are design principles that we can use? So the other aspect and motivation for this talk actually comes from a recent reappreciation of the strongly correlated electrons problems in solid. The original classical textbook example is high temperature superconductivity in the cuprates shown on the left here. I think that button is a little broken. Oh, it's my finger. Thank you. Yeah, right. Good. All right, problem solved. So here is an example of a copper-oxygen plane in a cuprate. So that might, for instance, be undomed lanthanum copper oxide as the very simple toy example. At low energies, we understand the system very, very well in terms of essentially strong electronic interactions for the dx squared minus y squared orbitals of copper. So to very good approximation, low energy physics is captured via a single band Hubbard model where you have a single band with a bandwidth that is much less than the electronic interaction, such that at low energies, we form a Mott insulator that then does very interesting things when we start adding or removing carriers. So from the perspective of theoretical modeling, there's an analogous real space description of this band picture that's going to be very useful. Namely, we should really be thinking about local Vania orbitals that are centered on the d orbitals of copper and are almost, but not exclusively, composed of the copper d orbitals. Interactions then in such a system are reasonably well screened such that we can focus on local interactions of pairs of electrons in the d orbitals, leading us to Hubbard model physics and Mott insulators. But more recently, there's been a reappreciation in terms of new classes of materials, particularly Moray materials, in which some of these approximations don't really hold. So the paradigmatic example, of course, is twisted bilayer graphene, which we now know has a host of interesting correlated electron phases that, however, emerge from very different low energy physics. So this is a cartoonish picture of the twisted bilayer, which at low energies gives rise to, now I think most of you have seen this many, many times, a low energy band structure where near charge neutrality, you form almost dispersionless bands. And so you can now gate tune the chemical potential for these almost dispersionless bands, yielding various interesting correlated phases as a function of Coulomb interactions. Now the problem, though, in contrast to the cuprates, is that if I insist on low energy physics only to be dictated by these almost flat bands and Coulomb interactions, the low energy description of interactions of correlated electrons in these bands, if I want to insist on a real space description, ceases to be local. So in fact, Vania orbitals for intrinsic or rather topological reasons, a fragile topological obstruction in these materials yields rather poorly localized Vania orbitals, which in turn, even for well-screened Coulomb interactions, yield interacting models that are relatively different from an ordinary Hubbard interaction, in as it entails crucially also longer range terms in the interaction vertex that give rise to more exotic or even topological phases. And of course, just to complete this phase diagram, the, again, rather better understood case of truly topological systems is paradigmatically the fractional quantum Hall effect, but also very recently twisted MOTE2 bilayers, which have been proposed to host fractional Chern insulating phases, where the low energy physics is now going to be dictated by quasi-Landau levels, flat bands with non-trivial topology, and no real space picture exists. So let me just acknowledge collaborations in which this effort, what I'm going to be talking about, sits embedded in. So this is my group at Penn, which is broadly interested in quantum materials and dynamics and has been thinking about generic themes of engineering non-equilibrium states of matter, dynamical controls, recently also cavity quantum materials, dissipative systems, and low energy correlated electron problems in transition metal dicot orgonite heterostructure. And this is embedded in a greater effort on Moiré heterostructures with Angel Rubio, who has given a really nice talk previously, and also collaborators, particularly in China, Leda Xian, who's been doing tremendously difficult ab initio calculations to characterize Moiré materials, and work at the Flatiron Institute and in Germany. So for the bulk of the talk, so let me now try and draw these two motivations together and argue why quantum geometry, and actually these new ways of thinking about correlated electron models beyond local Hubbard physics, can give rise to interesting new optical responses. So simplest example is optical absorption. Just imagine you have an isolated atom, and I'm thinking about coupling an atomic transition to light. Well, the naive model of this would be a dipole transition where I couple two states with different parity. And now in a crystal, I can do something very similar. Let me just draw two bands, and I'm color shading maybe an atomic orbital character of that band. My transition matrix element between these two bands will now be an interband transition in terms of the Bloch states of the band with a derivative of the Bloch momentum, which is really just the Fourier transform of a position operator in real space. So this already tells us that something interesting will happen from the momentum space structure of a Bloch wave function. And that's really the gist of thinking about quantum geometric reinterpretations of optical responses in solids, which has garnered a lot of attention in the context of free electron responses. Namely, quantum geometry can be thought of as really a geometric interpretation of the long wavelength structure of Bloch wave functions. So if I have a Bloch state and I adiabatically transport it to a small momentum point shift in the Brillouin zone, I can think about the overlap matrix element between two Bloch states in momentum space in terms of adiabatic transport via a Berry connection, which governs the change of the phase of the Bloch wave function. And you've all been known and loved from the context of Chern insulators and topological invariance, but also a Fubini-Studi metric, which characterizes the norm change of the overlap with non-abelian generalizations, and more recently also higher order geometric tensors under discussion. One more ingredient that I need to present in order to motivate the correlated electrons problem is that there's actually a very neat way of thinking about this from a real space perspective. So instead of Bloch wave functions in real space, we can talk about Vanier functions of a solid. For instance, here this is tungsten diselenide. We can pick out a single band of tungsten diselenide and try and model the physics of that band in terms of effective atomic orbital, almost atomic orbitals called Vania orbitals that form an effective lattice. Now, these Vania orbitals oftentimes are almost atomic orbitals, but not quite, and in fact have a finite spread that is usually very, very tight in many conventional materials, but doesn't need to be tight, particularly in Moiré materials. And the Vania orbital spread, just to make a connection to the previous slide, actually has a very nice lower bound in terms of Brillouin zone integrated traces of the Berry of the Fubini-Studi metric, which in turn is bounded by the Berry curvature. So this ties in a real space picture with the momentum space picture of the long wavelength structure of Bloch wave functions. Now in free electron responses, this has garnered a lot of attention in terms of trying to think not only about Hall effects, but also shift responses, which is a quantum geometric contribution to photogulvanic responses, circular photogulvanic effect, which is quantized, presuming that there is no disorder or electronic interactions, or more recently, resonant optical responses in solids. Now, this is a very incomplete list, so there's many, many more works that I just didn't have the space to present. But the correlated electron problem actually looks a lot less ambitious. In fact, I would argue that this is an almost complete list. So we have examples of fractional quantum Hall analogies on the lattice, actually work by Atach and Ajit Srivastava on looking at quasi-particle excitations such as excitons and quantum geometric contributions. And more recently, quite a lot of attention has been devoted onto flat band corrections, superfluid weight corrections from quantum geometric ingredients. So again, trying to understand superconductivity in graphene if we take the perspective that the band is almost perfectly flat. Now, graphene, of course, is not the only moire material for which this is relevant. We now have a host of other systems, such as twisted bilayers, mono or hetero bilayers of transition metal dichalcogenides, which have twist-tunable topological transitions, which are well characterized from ab initio, and also now have an increasing plethora of experimental evidence for both quantum spin Hall and quantum anomalous Hall phases. But so now let me bring optics back into the picture and argue why such systems are really, really hard to model, particularly for correlated electrons. So the very naive picture that we can take is, imagine you have a solid with a band structure that looks something like this. Here's your chemical potential, the dashed line. So this is my low energy band manifold in which all of the correlation physics of interest will play a role, take place. And then I have some band gap to higher energy inert bands, or I might also have lower energy inert filled valence bands that I really shouldn't care about at low energies. Yeah? And so the low energy, the ground state equilibrium, ground state is going to be dictated only by correlated electrons in these bands. If I insist on probing this using low frequency responses, terahertz responses, I should also expect that my optical responses should only be governed by the correlated electron behavior in these low energy bands. Yeah, and so this all seems relatively straightforward and intuitive. And of course, modeling this at very high energy scales is trivial. So we know light couples via minimal substitution. But of course, we're not interested in this parent Hamiltonian of condensed matter, which encapsulates all bands. We really want to know what is the effective dynamics and what are the effective excitations that we couple to. And so the name of the game is, we can think about, say, a single particle spectral function. These bands might form have a Mott transition, forming a lower and the upper Hubbard band, and I might probe transitions across the Mott gap. And so I should expect that my optical response at low frequencies is only governed by this. Yeah? And if I were able to construct such an effective theory, I could now address not just optical conductivity, but higher harmonic generation, or particularly new effects in optical driving and non-equilibrium responses. So this is unfortunately not as easy, and there's been a tremendous amount of work trying to even attack this problem on the level of free electron optical and nonlinear responses, and various benchmarks and ad hoc corrections for thinking about few band models of light matter interactions. So let me outline where the problem, or where we think the problem lies. So let me take a very theorist picture of, say, two bands near the Fermi energy and one high energy band split by a band gap. And now let me try and come in with very low frequency light. Right, so this is going to be tremendously off resonant from this high energy band. So I should expect any contribution to an optical response from this band should be suppressed by 1 over the detuning. Right, and so particularly as a theorist, I can take the very naive view and let me take just that band gap to infinity, in which the low frequency response should be rigorously only governed by these bands here. Yeah? Unfortunately, this is not quite as straightforward, so we really have to negotiate what that band gap and the structure of that band gap actually is. In particular, we can think about two different types of band gaps, one in which the two bands, so this is the band of interest and the inert high energy band, are composed of disparate atomic orbitals. But if we look at the interband current matrix element, so what is my transition matrix element for absorbing a photon and generating an interband transition? There's actually very old work from the 60s that shows this interband current matrix element can be rewritten in a very useful quantum geometric way as a product of the band gap times an interband Berry connection, which tells us, okay, here's actually where quantum geometry enters into the problem. But this immediately raises a problem, right? So because now I'm really, really detuned from this transition, but if my transition matrix element scales with the band gap, I can never ignore that high energy band, which seems wrong and defies physical intuition. Particularly, we can imagine a two-band system where I have a band inversion, where my interband Berry connection is going to be very sizable. So now my interband current operator scales with the band gap. So actually, before going to the resolution, let me just point out that this is even more problematic in a correlated electron system, but this is also what's going to give us some new physics. Now, if I have an interacting system, I can now envision a second-order process where I photoexcite a virtual excitation to that high energy band, even though I'm well detuned from that resonance, and then followed by a Coulomb scattering event that scatters this photoexcited electron off a second electron in the valence band, leaving 2 electron-hole excitations near the Fermi energy. And that matrix element is going to scale as interband Barry connection times Coulomb interaction times some band gap over band gap, which is order 1, even if the detuning is very large. So the reason, and just in terms of optics, this has a nice diagrammatic representation, but the reason why we're having such an aphysical process in our originally physically motivated theorist Hamiltonian of coupling light to matter is because we're really talking about the wrong basis, right? If I drive the system with light, I should not expect that the equilibrium bands of a solid still form an appropriate eigenbasis. And instead, what should happen, we think has a very neat physical interpretation in terms of the Vania orbitals that build these bands. It's best visualized in real space. So in addition, for electrons to couple to electronic, for photons to couple to electronic motion, if now my bands near the Fermi energy are composed of some Vania orbitals with a finite extent, then the photon should also deform the shape of the Vania orbital. And so the Vania orbital will start breathing in the light field. And that deformation of the Vania orbital is precisely what's necessary in order to cancel these spurious off-resonant contributions from higher energy bands. Now, it turns out this deformation has a really, really nice low energy description. Oh, is that a question? No. Low energy description in terms of essentially dressing the Bloch wave functions using a parallel transport factor. And there's a simple physical picture of what one actually has to do. So ordinarily, when we think about light-matter coupling in a solid, we might work in momentum space using a Bloch eigenbasis. We have an electronic state at momentum k, and then couple this to light. Yeah, that's our ordinary equilibrium Vania basis. This modification to cancel the spurious off-resonant processes actually amounts to not working with the gauge-dependent Bloch state at momentum k, but the gauge-independent Bloch state at momentum k plus shifted by the magnetic vector potential. This is a velocity gauge without loss of generality. And then parallel transported back to the gauge-dependent momentum using the non-abelian Barry connections of the bands of interest. So in momentum space, this amounts to a unitary transformation of the Bloch wave functions. But if you recall from the Vanier construction, the localization and shape of a Vanier orbital is a gauge choice for the phase structure. So in fact, that phase shift or non-abelian phase shift for the Bloch wave functions amounts to a real space distortion of the Vanier orbitals in the light field. And now generically, this effect will enter in materials, but will be very weak if the Vanier orbital is reasonably well localized on atomic sides. But if I have something like a Moiré material in which the Vanier orbital has a relatively wide extent, then this breathing motion can actually become the dominant response for a correlated electron system, which I'll hopefully convince you for one particular example. A theorist's way is to say that there's 2 gauge choices in the problem, and they're inextricably linked. So one more equation slide. What that means that the low energy problem is actually very simple. If we think about a velocity gauge approach, in addition to a usual pi-else phase for electrons on a lattice, we now need to account for the modification of these orbitals as a modification of the Coulomb matrix elements that the electrons effectively feel at low energies. So what we're really doing in an interacting electron problem is we're dressing the Coulomb interaction vertex using photons. So as my orbital deforms in the light field, the Coulomb interaction, or 2-particle Coulomb scattering, gets modified in a correlated system with non-trivial quantum geometry. And that's really can become the dominant effect in a system, particularly a flat band system, such as Moiré materials. And diagrammatically, this amounts to now having 2 types of light-matter coupling vertex, not just the usual paramagnetic vertex, but also a 2-particle scattering vertex and higher-order vertices for nonlinear responses. But OK, how much time do I have?
You've got 5 minutes.
OK, perfect. Plus questions or including?
9 minutes.
Good, perfect. So let me start by giving a very simple toy model for where one can see this effect. So this is something that we can solve trivially using many-body simulations and DMRG. This is an interacting 2-orbital chain that essentially amounts to a variation of the SSH model with a topological with a topological transition. Particularly, this model has a transition through a gap closing between trivial and Z2 topological phases, and in fact can host an exact flat band for a finite range topping model. But so what's neat about this model, and why we're using this as really our fruit fly as a first example of this effect, is that we can independently tune the dispersion of this flat band and the spread of the Vanier functions of the lower band. So again, we're forming a big band gap. We're going to be interested in putting our chemical potential into the lower band and asking about the correlated state at, in this case, half filling, although you can also think about this more generically. Okay, so what happens is actually the ground state is particularly neat in the inverted regime. Turns out one can show analytically this forms a bond density wave in the flat band limit, where the Vanier orbitals of this band are going to be localized, centered between two atomic sites, and are going to have an even odd filled, unfilled pattern. Now, we're not interested in ground state properties, but the excitation spectrum, which is also very easy to understand. If you have a bond density wave, the lowest energy excitations you can have are domain wall excitations, where you form a domain and an anti-domain here between even, odd, odd, even staggering of the bond density wave. And these domain walls in the limit of a flat band, this is somewhat analogous to the flat band superfluid weight discussion, can actually now exhibit dynamics purely from Coulomb scattering. Because if my Vania orbitals are not perfectly localized anymore, I can now have two particle scattering processes which can start to move my domain wall, giving the mode a finite dispersion. And so it turns out this is indeed what one sees. Yeah? So the low energy response is purely quantum geometric in nature. So one finds a domain wall excitation mode at very low frequencies. This is below the band gap to interband excitations, and has spectral weight that is a function of the quantum geometric tensor, or vice versa, the spread of the Vanier function. And in fact, the bandwidth of that mode is also a function of the quantum geometry of the band. Because the more spread my Vanier function is, the easier it is for two-particle scattering to move the domain wall mode. But so having tested this on a simple toy model, let me give one useful real materials ramification of this effect. In twisted bilayer graphene, the low energy bands near charge neutrality have commonly minimal descriptions due to a fragile topological obstruction in terms of so-called fidget spinner Vania orbitals. So these are Vania orbitals that are centered on the ABBA sides of the twisted bilayer, but the charge density sits in the AA regions. So these orbitals actually end up having three lobes being as delocalized as you would want. Yeah, so we should imagine that this is actually a pretty sizable effect. And just a sort of a quick crash summary of the low energy physics. These lobes are going to sit in the AA regions. The low energy Hamiltonian, by virtue of having extended orbitals, is actually rather extended. Turns out to be a plaquette interaction model, which gives rise to interesting phases that I'll discuss in a second. But let me just get to the immediate ramifications when I drive this with light. This is a 2.5 terahertz excitation at 20 kilovolts per centimeters. Precisely what happens is now that this orbital must deform in the light field. And since it's that delocalized over the length scale of a moire on itself, it will now start to breathe in the light field and thereby dress low energy interactions and potentially change the correlated phase. This is for linear polarization and circular polarization. We'll look at ramifications for the interacting problem in a second. So why do Coulomb interactions get changed is very easily seen from this animation here. So this is just schematically showing the overlap matrix element between neighboring electrons across different sides of a hexagon. Well, if I now think about calculating the Coulomb interaction vertex as a function of time, not only will my kinetic hopping matrix elements start to change because my orbital deforms, the kinetic overlap integral will change, but my Coulomb interactions will also start to oscillate. And this effect can actually dominate the low energy dynamics. So here for the largest fields, which is 35 kilovolts per centimeter, you find renormalizations of the Coulomb interaction by almost more than 50%. So two effects one could take from this. Let's just do the simplest thing possible. We're talking about going back to our initial motivation and thinking about Floquet engineering. The kinetic problem is relatively well understood. I drive a system periodically. I will start to quench the kinetic energy. The more interesting effect is that this oscillation of the orbital will now lead to an effective period averaged renormalization of the Coulomb interaction vertex. And in fact, the Coulomb interaction will decrease as a function of drive strength. But more importantly, there's a competition between a hexagon charging term and non-local Coulomb interaction terms that are understood to, or are thought to give rise to the phase diagram of TBG at low energies. Modulating TBG with light will start to engineer or change the interplay between the different competing Coulomb interactions, particularly suppressing or enhancing correlated hopping, that a charge neutrality can give you transitions from an intervalley coherent state to a competing quantum valley Hall state, or 3/4 filling, which is actually maybe even more interesting, can give you a transition from a quantum anomalous Hall phase that's observed in TBG to a proximal charge ordered phase at already relatively weak fields of what we're estimating is around 15 to 20 kilovolts per centimeter. So I think I'm almost out of time, so let me just do one slide on ramifications and what we're thinking about now and where we're going with this. So first of all, the lowest order question, aside from dynamical control, which might be relatively hard to achieve, is there something simpler to probe this mechanism? The simplest thing we could do is just to do time-dependent STM. Drive a system and try a simple, at least on the theorist's level. Can we watch the deformation of these orbitals? In practice, what you would see is that there's a charge density in the AA regions, for instance, for TBG. And the spatial extent of that charge density will oscillate in the field as a function of the quantum geometry of the lattice. But in the context of optical responses, there's more and more interesting ramifications. For instance, we can think about, again, the usual Mott-insulating problem of having a large charge gap and thinking about low-frequency excitations that emerge from magnetic excitations. Ordinarily, when people do terahertz spectroscopy, we'll couple the magnetic field component of a terahertz field to magnetic excitations. Now, in systems with non-trivial quantum geometry, just like Mori materials, the orbitals that host the local moments might actually be relatively extended. Yeah, and in particular, they might be so extended that different local moments have finite overlap with neighboring sites, which, if it now oscillates, starts to give us an electric field coupling to low-energy magnetic excitations. And similarly, we can think about Photogulvanic effects, for instance, just from taking this orbital deformation as moving the charge center of a Vania orbital and thereby driving a current. So just as a final and maybe more ambitious slide, we can ask, what are ramifications for microscopic modeling of light-matter interactions? And indeed, one thing that we'd like to do, but it's maybe a little more of an ambitious prequel, is to think about trying to extract quantum geometric ingredients directly from ab initio calculations to try and characterize correlated electron problems coupled to light directly from microscopic considerations and the crystal structure, to then combine with large-scale many-body solvers to understand to get a more precise understanding of correlated electrons responses at low energies. All right, so since James is already standing and I'm running out of time, let me just leave up my conclusion slide and open up for questions. Thanks for listening.